This is a recap of our Taylor approximation from lecture 5. Let's start back with the linear approximation. Remember, we've got some function fx. That's fx there. And we start by taking a particular, evaluating fx at a. So there we get up to that point. And then we draw the tangent from that point. And so that we have some value of x, say x1, close to a, then that value there is pretty close to that value there. So as long as x1 is close to a, we have a reasonable approximation. We can do a little bit better though by adding another term. This is our quadratic approximation, so we have a second term there. What that does is, instead of having a straight line tangent to our function at a, it gives a little bit of a curve, because we know a quadratic function is curved. We might call that px, that was a fx. So our approximation, px, is a little bit closer to fx for some value of x close to a. And we can improve that approximation by adding more terms. And that gives us the Taylor approximation. So where we have n terms, that's our nth order polynomial, or up to the power of n. And this is what we have there. So for any value of x close to a, we'll have a much better approximation. It might be something like that. So for values of x close to a, that's quite a good approximation. Values up here, of course, it would be not such a good approximation. That's our general formula. We can apply that, we'll look at a third order polynomial. So we'll just basically take this part of the nth order, so up to 3, a third derivative there. And we'll forget about any further terms. So what we'll need is the first derivative, the second derivative, and the third derivative of our function for a third order polynomial. The function we're going to look at then is this one. Y equals fx equals 1 plus x to the half, square root of 1 plus x, for x around some value, some arbitrary value a. So we'll need to evaluate our function at fa to get a starting point there, and that will just be 1 plus a to the half. We could find the first derivative to evaluate that at a, so that will be 1/2 1 plus a to the minus a half. Second derivative, evaluate that at a, it'll be minus 1/4 1 plus a to the minus 3 on 2, and our third derivative will be plus 3 on 8, 1 plus a to the minus 5 on 2. We have our third order Taylor polynomial there, so we can evaluate our function 1 plus x to the half is approximately equal to 1 plus a to the half plus 1 on 1 factorial is just 1, and we had our first derivative was a half 1 plus a to the minus 1/2 times x minus a plus 1 on 2 factorial, 2 times 1. Our second derivative then was minus 1/4, 1 plus a to the minus 3 on 2 times x minus, x times a squared. And our third term was 1 on 3 factorial. Or we could have that as 3 times 2 times 1 times 3 on 8 times 1 plus a to the minus 5 on 2, and then times x minus a cubed. We could evaluate that for particular values of x. What we'll do though is take a special case. We'll let a equal 0. Why are we doing that? Because for our purposes it's much simpler. We can see if we let a equal 0, then all these a's disappear. We'll have 1 plus x to the half is approximately equal to, 1 plus 0 to the half is just equal to 1, plus 1/2, 1 plus 0 to the minus half again is 1, times x minus 0 will just be x, minus, we had this minus sign there, that will be 1 on 2 times 1 on 4 times 1 to the minus 3 on 2, 1, times x squared, so that'll be minus 1 on 8 x squared plus divided by 1 on 6 times 3 on 8 times 1 again. X minus 0 to the cubed is just x cubed, so we'll have 1 on 16 x cubed. So the reason we let a equal 0 for our purposes is that when we're doing the calculations, this approximation is much simpler than this one. We could use other values of a. Let's have a look at how that works. Basically, what we've done is just shifted our focus from, instead of having a out here, we're taking a particular value there. And we're looking at evaluating fx around this point here somewhere. This is known as a Maclaurin polynomial. It's a special case. We've got the formula there. So the reason we're doing it is because the calculations are simpler. So let's go back to our example then. We have 1 plus x to the half is approximately equal to 1 plus 1/2 x minus 1/8 x squared plus 1/16 x cubed for x around 0. We can use that to solve particular problems. The one we're going to look at is the square root of 1.05. Well, that's equal to 1 plus 0.05 to the half. So we have x equals 0.05. So that's pretty close to 0. Our approximation should work. So we'll have 1.05 to the half is approximately equal to 1 plus 1/2 of x. So this is x, 0.05 minus 1/8 of x squared, 0.05 squared plus 1/16 of x cubed. And we can do that calculation, and we'll find that that's equal to 1.0246953, which is a pretty good approximation for the square root of 1.05. Now, sticking with our Taylor series or Taylor approximation about a equals 0, we had that fx is approximately equal to this part of the function, but there's some remainder there that if we add it on, we'll make, well, we called that px before, px exactly, so we've got equalities there, exactly equal to fx. So that's the remainder. That's the bit that we add on to make px exactly equal to fx. Now it can be shown using the mean value theorem that this remainder is actually equal to this function here. We have this extra variable in our remainder formula, so c, and it's some value between 0, so this is our value that we're taking approximation around, and x. So c lies in there somewhere. We don't know where it is, but our mean value theorem tells us that there is some c that will give us this remainder. We don't need to go into that proof, but it's there. What we can do though is sometimes we're not interested in the exact remainder, we're looking at the maximum value, and then we can choose a particular c. So let's look at our problem that we had. From our approximation, we had fx is approximately equal to our Taylor polynomial. We can change that to an equal signs and put in our remainder. So our remainder will be r4x, and then r4x will equal 1 on 4 factorial, the fourth derivative, evaluated at some point c, times x to the 4. Our fourth derivative of x is equal to minus 15 on 16, 1 plus x to the minus 7 on 2. So r4 will be, well, 4 factorial, 4 by 3 by 2 by 1. That's 1 on 24 times minus 15 on 16 times 1 plus c to the minus 7 on 2 times x to the 4th. Well, that's equal to, if we simplify this first bit, minus 5 on 144. The power here is minus 7 on 2, so let's just look at it like this. 1 plus c to the 7 on 2 times x to the 4th. So here we've got r4 depend on some value of c. So we've got that c there. We don't know what c is, but what we can think about instead is the maximum value of r4. R4 maximum occurs when c equals 0. So we're dividing by 1 plus c to the 7 on 2. The larger c is, the smaller this term is. Conversely, the smaller c is, the larger that term is. So if the maximum value of this term will be 1 when c equals 0. So we'll have the r4 max is equal to minus 5 on 144 x to the 4th. Actually, what we're interested in is the error. So that's the maximum remainder. It's also, we could think about that as the maximum error of our approximation. If we think about errors, we're not really concerned about the sign. What we would do then is take the absolute value there and just get rid of that minus sign. So finishing off that calculation, we had for x equals 0.05, r4, remainder for 0.05, take the absolute value, will be equal to 5 on 144 times 1 times 0.05 to the 4th, and well, that will equal to 2.17 by 10 to the minus 7, a very small number indeed. So here we have our approximation for 1.05 to the half. How close is that to the actual value? That's the maximum remainder, so that's the maximum error that we'll have.